special products are very simply just patterns that mathematicians have noticed in doing multiple iterations of distribution and factoring. So what we're going to answer in this video is exactly what is the pattern, where did it come from, how do you use it, and some tips for remembering it. The first pattern we're going to look at is the perfect squares pattern, and it basically has two forms. It's when I'm adding a binomial and then squaring, or when I'm subtracting in a binomial and square. And these are the two formulas that will result in those patterns. Now, where did the pattern actually come from? Well, let's take a look at an example. If you didn't know this pattern, you could still do this question or find that this result follows by basically just doing normal distribution or FOILing. If you use the definition of exponent to take the square and write it as two terms, then I'll just distribute my first a into the second binomial, which will give me a squared minus ab. Then I'll distribute my second term b into the second binomial, and I'll get minus another ab plus b squared. Now, when you go and combine your middle terms, you'll actually end up with exactly what this formula is. Similarly, if you did this for the additive version, you get the exact same expression. The only difference is that you'd be adding the middle term. So notice that a subtraction within a binomial squared results in the subtraction of a middle term, and the addition of a binomial squared results in the sum on the middle term. So now, how do we use it? To use these patterns, let's see how we can use it in both an example of distribution and an example of factoring. Now, the perfect square pattern is most easily used in distribution. Now, notice what happens. I have my first term, whatever my first term is, squared plus or minus the sum of the product of the two terms plus the last term squared. That happens every time I expand a perfect square. In this case, my first term is 2x. That's representing the a in this formula. My second term, b, in this case is 4, and this is a subtraction, so I'll be using the subtraction pattern. When I go ahead and apply this, this will equal my first term squared, which would be 2x all squared. Then, since it's a subtraction, I'll be subtracting a coefficient of 2 times the entire first term, which is 2x, times the second term, which is 4, plus my last term squared. When I simplify that all out, I end up with 4x squared minus 16x plus 16. Now, as you get faster and more familiar with this pattern, you technically don't even have to write out this middle step. You can say, well, 2x squared is just 4x, 4 squared is 16, and then 2x times 4x would be 8x, and double 8x is 16x. So then you can get straight to your answer in a very quick way. So perfect squares, the more familiar you are with the pattern, the faster you'd be able to expand them. Now, how do you use it for factoring? So that's a little bit different. First, you'd have to recognize that what you have is a perfect square. So how do you recognize that? Well, notice that in this perfect square, in either one, the subtraction or the addition, the first term and the last term both have to be perfect squared. The first term has to be a perfect square and the last term has to be a perfect square. Well, my first term is just x squared. My last term is just 3 squared. Well, now the question is, does the middle term also match the perfect square pattern? Well, if it does, then it would have to be double the product of the two terms. Well, x times 3 is 3x, and 3x times 2 would give me 6x. So this does, in fact, match the perfect square pattern, and since it's an addition, the only one that has an addition is when you're adding the two terms. So that would give me a plus. So this is x plus 3 quantity squared. This will also work for subtraction. If this was a minus here, then this would be a minus here. So the signs always match the middle term and the factored form.
Oh, I'm sorry. Did I break your concentration?
Another special product you should be familiar with is dots, which stands for a difference of two squares. It gets its name from this form of this special product, which is a squared minus b squared. That's a difference of two perfect square terms, and it factors to this. And again, this is derived from basically just using properties of distribution on my left-hand side to simplify it to my right-hand side. It can be used for expanding products and also for factoring products, an example of which is the following. If I have 2x plus 5 and 2x minus 5, these are conjugates of each other. The conjugates result in that difference of two square situation. So that's a quick and easy way for identifying when to use this perfect square pattern. And what ends up happening is it's just the difference of the first term squared minus the second term squared. So in this case, it'll be 2x squared minus 5. 2x squared, again, that exponent of 2 distributes to both of those values, and I'll end up with 4x squared minus 25.